Right, well, good morning, everybody. Welcome to another webinar. So turning into a tri-weekly event right now. Lots of people here, lots of good old friends from Virginia Tech, people from our group, and people I've known for a long, long time. So welcome, everybody. Welcome to all the newcomers as well. And today I'm going to talk about one of the most difficult topics in power supply design, and that's proximity loss. I've been talking about it for quite a few years, trying to find a way to have people understand how it works, and it's a difficult topic to present because the math is so complex, but at the same time it can be very accessible, and that's what we're trying to achieve with the models and the software that we're providing for everybody. So I hope sound is good, hope vision is good, and let's get started because lots to do here. Just some acknowledgements here. We've got John Beecroft is on the webinar with me here. He'll be answering many of your questions as we go through. John has worked with me for 20, 30 years now, teaching and watching my development of the proximity effect works. So thanks, John, and I'm sure he'll give you some good answers. Art Nace, I know, is on the webinar. Art has done all the programming for us to get from Ridley Works to LTspice to make proximity loss easy. So you just have to push some buttons. Dr. Vachi Vorparian, I've known him for many, many years, and he helped me with circuit analysis, fractal networks, and so on that we looked into for doing proximity loss. And Dr. Kichen Yang was one of our interns last year, and he derived a lot of the algorithms for us for solutions for the proximity loss circuits that you'll see the effect of that later on. Going back in history, we have Mr. Dowell, who did the effect of eddy currents and transformer windings in 1966. So this is not a new topic. This is now 54 years old, and his paper was the culmination of work that started actually in the 1930s. I'm trying to figure out why transformers were hotter than people expected them to be. And then there's another important paper for years we were on IEEE from 1993. A lot of this work has been done before in a different domain. It was in the power delivery domain, where they found equivalent networks for proximity loss, and actually surprised us that they did the exact same models that we're about to show you, exact same order, the same ways of doing it as we did. But we didn't find that when we were doing the original work. But it's actually a really good thing, because if you got now you've got two people at least coming up with the exact same results. So you can know that it's solid. It's in the IEEE transactions on power delivery. Nicola Rosano, shout out to him, because he did a 7th order network for this, and he actually alerted me to the earlier work on the proximity losses. And Dr. Glenn Scott, who I was at school with Virginia Tech, who helped me through Dowell's equation. And yes, I need help. And it's not an easy topic. The math is hard. And let's talk about that a little bit. Here is some of the math for Dowell's equations. And this is the reason why most people don't even go there. Because when you look at this, I mean, who remembers hyperbolic sines and cosines and so on, and can even figure out what these functions look like? But this is the starting point for doing proximity loss. So the equations you see at the top here in red and green, the basic Dowell's equations, and then there's any number of highly advanced, anytime I see a double integral, I feel slightly ill. Highly advanced papers to find refinements on Dowell's equations and add Bessel functions to Dowell's equations and so on. And I don't know, if you start with this in magnetics design, it really steers a lot of the industry to say, well, I'm just not going to do that because it's too hard. And I completely sympathize with that. But you have to remember something, you know, we're engineers. Most of us are not pure researchers. You know, if you're doing a PhD dissertation, you know, by all means, go for it. Maybe. but don't get lost in the math if magnetics, advancing, fine analysis of magnetics is not what you're writing about, because it does distract from getting the work done, which is winding a better transformer. That's what we're all trying to do. So first thing I'm going to tell you on these equations, just forget that you've seen them, because you don't need equations. And if I can, this is kind of like the equations for a transistor or a FET. They're very complex. Schrodinger's wave equation is evolved, things that, most of us can't understand, but just because you haven't been into the math doesn't mean that you can't understand how to use a device. So in the transistor world, we all know how to read the transistor curves. And then beyond that, we all go from the transistor curves to splice models, and we can all use the results. And the exact same thing happens with Dowell's equations and magnetics. You don't have to know the math. You have to know what the math means to you and what it looks like at the end. So the next step in this, say, okay, forget that. And trust me, I can't remember that equation either. But these curves here they form one of the most elegant charts ever made for producing magnetics, which is a complete summary of Dowell's equations for every situation that you might run into, where there's a symmetric type structure of windings in windows. And they've condensed it down to one set of curves. And I don't know who first published these curves. These are Dowell's equations, normalized curves. I don't know who first published these, but engineers in the 60s and 70s and 80s knew how to use them and how to wind better transformers. Most engineers today either haven't seen these curves or are really confused about how to read them. And we're going to try and unravel that a little bit, because engineering design shouldn't be about working equations. It should be about how do you manipulate these curves to make the impedances, resistances look exactly as you want them to. So something to know about the normalized equations, there's at least there's 2 or 3 levels of normalization going in here, which makes it very confusing. So on the x-axis here, this is not frequency. This is the height of the winding divided by the skin depth. And the skin depth is square root of the frequency. So 1 over the square root of the frequency. So you've got 2 decades of curves here, which doesn't seem like a big range to cover everything we do in magnetics, but it's because it's not actually plotting versus frequency. So there's that normalization with respect to frequency, the square root of it, which is a very strange thing to do. And then there's the normalization with the height of the winding. So as you change the height of the winding, the curves are going to shift. And then on the left-hand side is the AC resistance with respect to the DC resistance. And of course, as you make a winding thicker, you're going to change the DC resistance, you're going to change that ratio, but you're also going to change, the height relative to the skin depth. So we've actually got a triple normalization in these curves. And that is the source of, people these days not knowing quite how to use them. And I don't think any of this is taught anymore. How do you read a curve? How do you manipulate the curve? Because everybody has computers and they think they want the equations, they want to manipulate the equations, and they don't learn the art of shifting curves around. So that's what we're going to talk about, in some detail for an example today. So everything is explained in these proximity loss curves. And they're very compact and elegant. This is all you need for most of your transformer designs. And they show what happens to AC resistance as you increase layers from half a layer to 1 layer to 2 to 3, all the way up to 20 layers here. And we can keep on going to, 100 layers if you want to, which comes useful for Litz wire if you want to. So it shows you some things here that as the number of layers increase, you're increasing the AC resistance of your structure. Perhaps when you look at the curves for this first time, they're overly elegant in that you can't see the design direction when you first look at them. Because when you first look at these curves, the conclusion you'll come up with right away is that, okay, if I use more layers, things are going to get worse. And there's no benefit to that if I use multiple layers. And that's because the normalization is respect to the DC resistance. It misses the point that when the layers goes up, the copper thickness goes up, so the DC resistance goes down. But on this curve here, the low frequency part of the curve doesn't show that coming along. So perhaps that is a way that sort of obscures these curves a little bit. And it's very difficult if you're just starting, if you haven't had curves explained to you, how you're going to manipulate these curves and make them do what you want to. Notice I'm not talking about equations here. I could talk about manipulating numbers, but that wouldn't mean anything. You have to have a picture. You have to have the plot. And there's many places on the internet where you can go pick up these curves. You can get it from our software, of course. You can come onto our group on Facebook, and we have a file listing there for generating these curves. Lots of different ways for you to do this. Let's take away one of the normalizations. And the first one we'll take away is that we'll plot this AC resistance over DC in terms of frequency, not in terms of 1 over the skin depth. So because the skin depth is root frequency, when I change the curve to actual frequency, we now see that the curves go over 4 decades. So we can start at 1,000 hertz, 10,000, 100,000, 1 megahertz, 10 megahertz. And now you see how those nice compact curves are covering 4 decades, which covers pretty much all of power electronics. There's some people trying to go above 100 megahertz, not too many. There's not too many going down below 1 kilohertz, though, in the high frequency power conversion. Obviously, this work started for line frequency transformers, and then you can just renormalize that as you want to. But this is a particular unwrapping of the normalization. We centered it around 100 kilohertz, and that's for a 29 gauge wire. So now it's become specific to a 29 gauge wire at 100 kilohertz. If you don't do that, you go back to the unnormalized curves. But, even on this curve, we can see the effect of adding more layers is bad out here. We can see where the curves start lifting up. So if you do a half layer, that would be a interleaved winding. It doesn't start lifting up until 300-400 kilohertz. 1 layer, it's just beyond 100 kilohertz. 2 layers, you can see substantial increase. 20 layers, obviously, you've got more than 10 times the resistance at 100 kilohertz. So now we've turned these into specific curves centered at 100 kilohertz for a 29 gauge wire. And what can we do with these curves? Well, we can manipulate this break frequency with 2 things. The number of layers we put in, obviously it curves up earlier with more layers. And then we can manipulate it with the thickness of each layer. So the thinner we keep the layer, the more the curves shift over to the right.
Good question from later on there, right?
Okay, we have a question. Go on.
So if the core current had DC and AC components like in a Ford converter, is the AC resistance affecting losses only for the AC component or for the entire current?
Yeah, that's a really good question, because yes, we've got these nice curves that show you what the AC resistance is doing, but when we build a switching converter, you have all different components in there. So you have DC component, you have the 100 kilohertz component, if that's your switching frequency, then you've got 300, 500, 700, 900, it just keeps on going. So every topology has to use these curves differently, because it will hit the curve at different frequencies. And then you've got to multiply by the AC resistance at that frequency times the RMS current at that frequency. And now you've got this horrendous convolution of the solution to Dowell's equations, which are bad enough, but then you've got to extract the Fourier transform of the waveform of the converter that you're on, and every converter is different. So if you want to see that done in all of its gory detail, you go get the book by Hurley, Professor Hurley. I do recommend you get that. It's an online book that you can download, and he actually goes through and solves all the harmonics of a particular set of converters, and then he does a convolution of that with the AC resistance that comes out of Dowell's equations. That's great for writing a book. I don't recommend that. Spice is going to do that for us. It's very good at doing that. So, but that's what you have to do. So when you design a transformer, we're going to see this for some of the modern designs for inductors as well. The solution that's right for one particular 100 kilohertz converter may not be the right solution for a different one. So if you've got a full bridge primary, it's different to a 2-switch forward primary. And that's different to an LLC converter primary. So you're going to wind them differently in different cases. And hopefully that will come across when we do these examples. So we've got our little levers to move these curves here. We've got the layer thickness, and then we've got the number of layers moving this up and down. What's missing from these curves, again, because of the normalization, is that when we increase the thickness, yes, we shift the curves left, but the DC resistance drops, and that's not shown on this normalization. That's why these curves, I think, are a little bit confusing, and then we have to get more specific into a design to start unraveling the curves to see how they work for every particular converter that you use. Notice some characteristics, by the way, when we're plotting versus frequency, the curves always end up with the same slope. All these curves are parallel to each other at high frequencies, and their slope is going up with 1/2 of the frequency. So you go 10 times the frequency, you only go up 10 dB in AC resistance. So you go 100 times frequency, your AC resistance would go up by 10. That's the final asymptote at high frequencies. But then there's a transition region asymptote here, which is a slope of 2. So when you go 10 times the frequency, you actually go 100 times the AC resistance. So you get a rapid climbing of AC resistance in this region here. So that, you can see on these curves here, it's falling right in our switching frequency region. So now you've got difficult decisions to make about, do I layer my windings this way or that way? Do I use foil or wire or bifilar and so on? That's all the tools you have for manipulating these curves. And we're going to see some specific cases coming up soon. Okay. You flag me, John, if there's more questions I should catch. All right, let's bring this to life a little bit. And this should answer the question you said. This is a 2-switch forward, 150 kilohertz forward converter. Input voltage is 500 to 700 volts. So this is an industrial type application. Very high input voltage. That means lots of turns on the primary. So in this case, we're going to end up with 116 turns on the primary, and we're going to have 7 turns on the secondary for a 12 volt, 15 amp output, and 150 kilohertz, as I said, is the switching frequency here. And we're going to look at 3 different windings. So there's different ways to wind this. The first way to wind it is say, well, I've heard that lots of layers is a bad idea. So let me do 1 layer of windings across the bobbin. And then, of course, you don't have much space to fit in. So you got to get 117 turns in there. That means a number 36 gauge wire. Now, it's a pretty tiny wire. That comes out with 2.8 watts if you use a number 36 wire. So then you say, well, what if I do 2 layers of windings? You know, we've looked at the proximity curves. Well, 2 layers is not going to be good, but I can now use a 29 gauge instead of a 36. And notice, in theory, this is 6 gauges. That's double the size. In practice, it's not, because you've got to choose the nearest gauge that fits inside the bottle. Okay, so there's a rounding there that goes on. And this says, okay, 2.8 watts will drop down to 0.59 watts if you do only DC analysis. If you go one step further and you say, hey, let's do 3 layers because this is looking better. So, okay, 3 layers of windings in the window. That's 0.385 watts. So conventional DC analysis is saying, well, 1 layer's not very good, 2 layers is better, 3 layers is even better than that. Why not keep on going? Which is in complete contrast to proximity loss analysis that says number of layers is bad. So they're kind of pushing and pulling on each other here, and you've got to find the right number of layers for this. And we're going to go in now, we're going to generate these cases. Do something live, which I might regret, but we'll see. Okay. I saw my software just restarted itself, so hopefully that works. Pause. This is always the worst nightmare, of course, when something happens in the middle of a webinar. Okay, begin design. So here's our converter. Let's look at our output voltage, make sure it's regulating. There you go, 12 volts output. And now let's go look at our transformer design. And sorry, let me start on the primary winding now. So you come in here, and we're using, I think it's an EFD 30 core. And we say, okay, let's start with a 1-layer winding, because that's the easiest to wind. It's the safest with high voltage, because the voltage extremes are opposite ends from each other, and we know the proximity loss is going to be low. So this is our 36 gauge wire case. And we can see here we've got high loss, 2.8 watts. We'll do that. Let's go and sweep our AC resistance. So here we go.
Solving Dowell's equation for transformer primary. 10 kilohertz.
We put a talking part in the software here that you don't have yet, those of you who got the software. So when you're waiting, it lets you know where it is. Okay.
Solution complete.
So there you go. There's your solution to Dowell's equation. Let's clear out the old data that's in here. There you go. So now we've taken that normalized Dowell curve, if you will, and we've shown it for the actual case. So we see this is not AC over DC anymore. This is actual resistance of the winding. And it's starting just below 10 ohms. You fill the screen up here, sorry. We're starting just below 10 ohms. And we can see that the resistance is flat until we get out to about 500 or 600 kilohertz. So we've used a very thin wire. So we've got good AC resistance characteristics in here, except that we've got 8 ohms of resistance in the circuit. So that's going to penalize us because one of our harmonics on the primary current is DC. So that's going to hurt a little bit. So let's save that data set. Right there, we saved it in red. And now let's go look at the primary winding again. Say, hey, let's wind it with 2 layers because I don't like that 2.9 watts. Let's go 2 layers. And that now comes down to 0.5 watts with DC calculations, 0.9 watts with AC. Let's go look at the curve again.
Solving Dowell's equation for transformer primary. 10 kilohertz. 100 kilohertz. 1 megahertz. 10 megahertz.
Okay.
Solution complete.
Now we've done the thing that the normalized Dowell's equation can't show us. They showed us that at high frequencies, the 2-layer winding is worse. What they didn't show us is that at low frequencies, this is actually 4 times lower resistance. Why 4 times? Because you got twice the length, so you can use twice the diameter wire. That means 4 times the area, 4 times less resistance. So now we see the curves from, Dowell's curves. Here's the 1-layer case, here's the 2-layer case that does go up much steeper in this region here. At high frequencies, the 2-layer case is worse, but at 150 kilohertz, it's still much better than the 1-layer case. So you certainly would think about doing this 2-layer case here to get the losses down. So now you can see how we've unwrapped the curves. We've pushed on the number of layers, we've changed the thickness of the winding, and now we've got a lower loss solution by doing this. Great. Let's save that. That's the 2 layers. And let's go for one more design, which is 3 layers. Now this gets us to 27 gauge wire. And the DC losses drop again. And then the AC losses, can't remember where they were before. Oh, they've gone up. They've gone up on the AC losses. So let's sweep the AC resistance again. So go.
Solving Dowell's equation for transformer primary. 10 kilohertz. 100 kilohertz. 1 megahertz. 10 megahertz. Solution complete.
Okay. Now we've got our third solution for the problem. So let's save that as data set 3. So you see what we're doing here? We're not thinking about equations. We're just thinking about how do we shift these curves around. Okay. So there's the first case. And then there's the second case with 2 layers. And then there's the third case. The DC resistance drops, but the AC resistance climbs quite a bit in this switching frequency here. And in the harmonics, of course, it's going to be worse now than the single layer case. So at 300 kilohertz, now we've got 13 ohms instead of 8 ohms of the single layer case. So it's not entirely clear which one of these is going to give us the best solution. But you see what we're doing now. We're playing with windings and layers, solving the problems, looking at the curves, and then deciding what we're going to do with the design next. So let me go back to my PowerPoint to figure out what we're going to do with this next. So there's our 3, that's actually a 4th solution in there. We'll get to that one in just a moment. What are you going to do with this information? So this is, you've solved the equations, you've got the curves, or you've just read the curves and unnormalized them through whichever method you want to use. Now we've got the tough part is we've got to, the hard way to do this is this. You look at the waveform, it's got DC, 100, 300, 500, 700, as far as you want to go. And of course, this is linearly decaying with frequency harmonics for a square wave. As the pulse gets narrower, you'll see some bumps up in the higher harmonics that don't go linearly anymore. If you want to do this the hard way, it's Hurley's book reference, you find the DC component by Fourier analysis, and then you find the first harmonic by Fourier analysis and multiply by the Dowell solution at that point. Then you find the third harmonic and the 5th and the 7th. So you're repeatedly solving Dowell's equations at all these points, and then solving the Fourier transforms at that point. And of course, you know, if you change your circuit a little bit, you add some magnetizing inductance, things like that, the whole circuit changes and the whole harmonic structure changes. So, you know, you can only solve a relatively simple case doing it this hard way, as I call it. Any questions, John, I should look at?
It's one about winding distribution.
Okay, well, let's keep going and we'll get to the next part of the solution. So what we're going to do next is say, okay, this is the curve of resistance I get. Can I build an equivalent circuit that will give me that curve? And our equivalent circuit looks like this. Okay, and this circuit has been named in the past. I can't remember what it was. I kind of hit upon this after doing work with Fourier and his fractal networks, and then incidentally discovered the same circuit that other people have used for this kind of thing. And it's got 5 inductors in parallel with 5 resistors. So think about this now, just intuitively, don't go do math on it, just say, okay, well at DC, all the inductors are short circuits. So at DC, I've got the DC resistance. Go up in frequency a little bit, and then that AC inductor there starts opening up relative to the resistor, and at that higher frequency, you now have to flow through that resistor as well. And you can see the size of these resistors. The first one is 1 ohm. The second resistor is 25 ohms, and then 50, 142, 400, and 403 ohms. So these resistors climb rapidly. So at high frequencies, the current has to flow through all the resistors. At low frequencies, it just flows through the DC resistance. Okay, so we can match the circuit with this network. And the surprising thing, you know, after we tried 3 networks, maybe other people hit on this network first time, I don't know, is how well it matches. If you look at the yellow curve here, underneath it is a dashed purple curve. And the dashed purple curve is the match of the equivalent RL network. So this is the real part of the impedance. This is the theory in yellow, and then the purple is the matched network. Okay, so now we've got a circuit which matches exactly what the impedance is going to look like. And we're sort of doing this in the frequency domain now, but now you can take that frequency domain circuit and simulate it. So we're going to ask LTspice to do the hard work of hitting this with the actual converter currents and then figuring out where the currents are going and what kind of dissipation you're seeing in each of the resistors. Okay. Mathematically, by hand, it's a nightmare. Okay, I don't recommend anybody try to do that. By all means, look at Hurley's work and say, okay, look, somebody did that. But as soon as you add a little complication, then you know you have to start all over again. It's a lot of mathematics, and there's just an easier way to do it. So let's okay. And just for those that care, this is our relative error of the equivalent network versus the real solution to Dowell's right here. And you see it oscillates back and forth with a 1, 2, 3, 4, 5th order network right here. And we're less than 10% error. Now, one of our group members, whose name I gave earlier, he did a 7th order network and he got it down below, I believe, 2%. So if you're obsessive about that last 2%, great. But really, what are we looking at here? Well, we're looking at resistances that are multiplied by a factor of 10. You know, 10% error in that is not a big deal. Okay, so we don't need to refine this further when they do Bessel functions and things like that. You know, to me, it's a little bit of overkill. You know, just get on with it because something's going to change in that structure that you build that isn't modeled properly anyway. So we solved the Dowell's equations. You can do that by reading the curves and extracting the data from the curves. Then we fit the AC resistance to match that. And let's go do this live just to prove it works. So we go into our program here. And the last solution we've done is the 3-layer solution. Okay. And we go back to our schematic and we say, okay, let's kick that model out to LTspice. Click on here. And it says okay. And then we go into LTspice. Sorry, let's open that again so we get a clean file. Go into LTspice and you say, okay, give me that 2-switch forward webinar circuit right there. Here is my AC resistance for the transformer. Inside that block are these numbers here, which are passed over directly from our software. And I have a lot of thanks here to give to Art Nace, who facilitated this transfer. You know, believe me how important this step is. You know, we didn't derive these models first, somebody else did. But the step of looking at the winding structure, clicking a button, and putting the circuit models, the elements, into LTspice with no work on your own is huge. Because if you have to type these in individually, you're just not going to do it. We're all too busy. We've got circuits to build. Okay, so it's dumped the models into here for us. Let's see what happens when we run a simulation on this. And we do this 2 ways, by the way. We do this into LTspice and we do this into PSIM. Sometimes PSIM goes too fast. You click the button, boom, you got it all there. And it's like, I like to see LTspice doing its work sometimes. So let's watch that happen here. So here's our simulation of the output. You see it chunking up there. The circuit is coming into regulation up to that point. And this is a very high order circuit. We've got 5 L's in the RAC in the primary, 5 in the secondary, 5 for the inductor. So there's 15 L's in the circuit. A couple more from the power stage and some C's. So this is almost a 20th order network that's being solved here. And you see it doesn't take that long. Let's go look at the primary current. Okay, so you see here it goes up and then comes down into regulation. We can zoom in on that current there and we see our switch waveforms. Okay, so you see here it's not, there's a little bit of negative because there's actually some reset current flowing. So LTspice is going to go beyond any theory. It's going to actually calculate that reset current going back in. More harmonics coming in from that. Now let's look at the dissipation. So you hold the Alt key and you click on the primary resistor right here. Let's get rid of the output voltage, don't need that. Delete output. Here's our primary AC dissipation. And you can see here, this is 380 milliwatts. So if you're only doing DC calculation on your transformer, this is the number that you got. So you go in carefully and you extract the RMS, and then you do I squared R times the DC resistance. That's the number you're going to pull out. You can say, hey, that looks like a pretty good design. It's 200 watt converter and there's only 300 milliwatts in the windings. But let's now look at the AC resistance. Click down here, click a little thermometer on the AC resistance right here. And you can see the interesting shape of this. It's got spikes at the edges because that's the high frequency hitting a very high resistance. So you see these spikes. And now you ask LTspice, click control. And it says, no, it's not 300 milliwatts. There's an extra 1.9 watts in that winding that you're looking at. Okay. So this is the power of using Spice to do this work for you. Yes, we generated the curve of the AC resistance that came from solving Dowell's equations, you know, or it came from just reading the curves and translating those on normalizing those. Then it runs the AC waveform through there and it automatically multiplies in the time domain every harmonic times the resistance at that frequency harmonic. You don't have to do a post solution. You don't process the waveform, extract the harmonic, multiply by the AC resistance. This is done in the time domain. So that frequency domain network, changing the resistance in the frequency domain, it works just fine in the time domain here as well. So you can see now that we have 2 watts of loss in here. If you add this 1.9 with the 0.3, I think it was, versus just the 0.3 watts of loss they expected. So 7 times the loss in the transformer. And any of you who've been involved in power supply design for a long time, the one constant you know is that the transformer windings are always hotter than you think. And they will surprise you as the turns count goes up and your power levels go up. You know, the amount of heat that's generated, if you're not doing proximity loss, you know, you're going to miss these effects inside the winding. So this is really important to know about. And I hope we've made it easy here so you can see it. Let me go full screen on this. I'm trying to look for the power scale. I think it's on the right here. I can't see it. There we go. So you see these pulses of power here. There's like 250 watts on that sharp edge. Okay, that's where you're hitting the hard edge on the current waveform, and it goes through, what is it, 500 ohms for a very short period of time. That's where these spikes are coming from. These are not LTspice simulation quirks. These are actual dissipation in that network during that period. So this is kind of cool. I like this. Go, John, no question?
Or warm.
Warm, yes, it's going to be warm. It's going to be warm. So this is a case where going 3 layers is too far. 2 layers is about the right number of layers in here to minimize this loss. But we're doing everything now. No, not looking at the curves. We just go into LTspice. And we make a transition from, you know, the winding to LTspice really quickly. So if we want to change that winding, so what do we get here? We got, that was 1.9 watts. We say, okay, well, let's do another design. Let's go primary winding, and take it back to 2 turns. And just for the hell of it, I'm going to split the winding at the same time.
2 layers.
Right, I've done 2 layers, split the winding. Okay, we all know, we all heard splitting winding is a good idea. Notice the predicted loss in here with proximity is 0.65. This is not complete. This is not all the loss. This is just an assumption that everything's at the switching frequency, which of course it isn't. Let's go solve that AC resistance again.
Solving Dowell's equation for transformer primary. 10 kilohertz.
Since we've had a program talk to us, I actually find it kind of reassuring
1 megahertz.
being told what's going on.
10 megahertz.
It'd be like that too.
Solution complete.
So here's our next solution. So we started with 1 layer, which is the red curve. We went to 2 layers, which was the blue curve. Then we went to 3 layers, which was the yellow, and that was giving us quite a bit of anticipation. The best curve we get here is the 2 layers split, because this is like 2 single layers, okay? So it doesn't start lifting up until here, and then you can see this is lower in every region except for this DC part here. All right, so that's the case we're going to look at next. Go back to the schematic, do another design case. There, all done. Go back to LTspice. File, pull up the file again. There we go. Our new elements have been put in here. We've wound it differently, so the equivalent model, these values here are different from what they were before. Notice that first resistor is now 4 ohms, used to be 25 ohms with the previous model. So let's run it again. You know, I'm becoming quite attached to LTspice, but it didn't happen until I automated this circuit transfer. You know, if I had to type in circuit values, I didn't like it that much. But let's see, here's our current coming to steady state. Zoom in on the current. Now let's go straight into looking at that AC resistance again. Right there. So these are our AC losses. Click on that. Now we're down from 1.8 watts to 200 milliwatts, okay? This is almost 10 times improvement just by layering and doing different layer count, okay? So yeah, proximity loss is really intimidating, but these are powerful tools that it gives you. These are not subtle refinements, okay? This is a 10 times loss reduction. Right? When you know how to bend those curves around, about bending the curve, right? We talk about flattening the curve. We're bending the curve. That's engineering. Okay, you get this 10 times improvement. Not many engineers have this skill. Okay, not many people know how to manipulate their magnetics and then solve the transformer design in this way. And I'm sure at your companies you have the magnetics guru, and he's kind of like a god. Or she is kind of like a god and has been there for probably about 50, 60 years. They know these things. They may not use proximity loss, but they have learned how to shape those curves. And you can't learn it unless you do it. You have to go in and you have to measure things, and then you have to build the circuit and watch it get hot. And the profound effect of this doing this will then come home to talk to you. And you'll really move up your level of design when you get used to this. Okay, jump into PowerPoint again. So here, this is what we've done. So we've had LTspice do all the hard work for us. And we did 2-3 designs inside our Ridley Work software. We put 2 of them out to LTspice. We got through that in, what, 20 minutes doing all of that while I'm talking at the same time. This is work that we used to do the hard way 30 years ago by hand, would take weeks to get through this. Okay, so this is a really good skill to start to learn. Approximately, and then here's our calculations on this one. This is the case we just ran. So this is the DC calculation and the waveform, and then this is the AC calculation. So here's my scale here. You can see that. This is the 1.8 watts versus the DC calculation. So if you're not doing proximity, if you're above just a few watts of power, 5-10 watts of power, this is the kind of effect that you're missing And you don't really want to miss this when you go to your first breadboard. Okay, you don't want to size that transformer and do a PC layout, and then suddenly you've got 10 times the loss you expected. Okay, so yes, this is hard. The math is hard, but once you get this concept, it's like, I don't need to do the math. I work with the curves, and then it's all about practicing with those layers. Then you become a designer. You know, you're not an analyst. You're not a researcher in the analysis and the math. You're a designer of the windings. That's where the power comes to you in this. All right, this is an interesting case, and I know we have at least one person from Coilcraft on this webinar. Can't remember who that is, but I saw them show up. I think we have someone from Worth on here too, but pay attention to this, because this is one of these new planar winding inductors that every company is putting out. They're really nice inductors if you're building a buck converter. Okay, so let's go look at the inductor and go back in our software again. Let's go to the inductor design. And this is a 15 microhenry inductor. Here it is, by the way, on our board. Hope you can see that. I can't see my own image here, so let's see. Here's a 15 microhenry inductor in this, I think it's a 400 watt or an 800 watt buck boost converter. So we're using the core from Coilcraft. They've numbered it SER2918H. This is just the core right here, and you see it's a gapped ferrite, gapped in the middle right there. We've taken the windings off it. And it needs about 7 turns on it. We're pushing a bit on the flux density, but that's okay. And let's look at our winding options now for the output inductor. So buck converter output inductor has the characteristic of very strong DC current. That's the 15 amps DC. And then just a little bit of ripple current. It's 0.9 amps RMS. That's about 2 or 3 amps peak to peak at this low line condition. So there's not much AC current going on. There's lots of DC current going on. So we can look at, starting as we did the other one, a single layer design, which is 19 gauge wire, which is 1.75 watts. And then we can look at a 2-layer design, and then which is 0.75. So let's see, we went from 1 layer, which was 1.7 watts, 2 layers is 0.75, so it's about a 2-to-1 reduction with an extra layer. 3 layers, it goes up again because we kind of run out of headroom. We can't make the winding actually bigger. So the lowest loss design we can get with wire in here is 0.75 watts. Now we look at using the helical foil, which is the structure that's going to go into the windings here. So it's wound like a spring or a slinky in there. Let's go to helical foil. Oh, look at that. So 0.75 watts is cut in half to 0.367 now. So that looks like a good design. That would explain why companies like Coilcraft and Worth are heading in this direction. Everybody's providing these, you know, flat wound inductors to do the job. Let's click go.
Solving Dowell's equation for inductor winding. 10 kilohertz. 100 kilohertz. 1 megahertz. 10 megahertz. Solution
Okay.
complete.
Let's get rid of this winding here, clear that data set. Okay, so this is the one we just ran. So it's helical foil. It's 3.8 millimeters across the window. And this has the interesting characteristic that even though it's a stack of turns, looking from the inside to the outside of the bobbin, this is actually a single layer design here. So even though it's designed for high frequency, you can see that the resistance is climbing from a very early point because the thickness of that wire is 3 millimeters. Before we were talking about, you know, 20 gauge wires, 19 gauge, 29 gauge wires. We're way beyond that. So the corner where the AC resistance kicks up is quite low here. But of course, we've got mostly DC in this. If I look at my switching frequency, the resistance is 33 milliohms the DC resistance is 1.5 milliohms. Okay, I know it's a little bit lower than the data sheet. That's because we used a thicker foil than they used in the real product. Okay, so you've got that extra flexibility in there as well. All right, so let's go take that there. And what are we doing? 1050 here. Let's, all right, we already swept that. I need to do this. Sorry. Back to the schematic. Go to Spice Launch again. Right there. Yes. Go back into LTspice. Pull in the model again. So it updates the model. Run the simulation again. And we're going to see that this inductor is let me look at my current. It's right there. Stop. And now I will zoom in on the current, and I will look at the AC power right here. This has only got 32 milliwatts of AC power. Okay, that's because there's very little AC current flowing at that frequency. And then everything basically is DC dissipation. Okay, so here's the DC dissipation, and that's the 0.75. This has got resistors gone up. Something happened there in the transfer. I'm not sure what that was. I obviously changed something. But all the losses here are the DC resistor, not the AC resistor. Okay, and that's because we're on the output inductor of a buck converter. Okay, let's go back in. Look at this here. Inductor design, and then the AC models. This is my AC model. Sorry, let me draw the values. So the values again, click on that. This is the AC model. I have to refine this because we're not quite where we should be there. I see a discrepancy in that resistor. This is the AC model for that coilcraft part once we get those thicknesses done. Okay. Now we can go in, look at the winding again, and say, well, what if I didn't use that kind of foil? I used regular foil in here, and sweep the AC resistance again. I'm sorry, I'm not sure I saved that last one, but we'll find out.
Solving Dowell's equation for inductor winding.
Right, so we've taken the foil now, we flipped it 90 degrees to wind it more like a conventional transformer winding.
1 megahertz. 10 megahertz.
Okay.
Solution complete.
And now we look that we've got the 7-layer winding here versus what we had before. So I've lost that one, so maybe save that. Let's sweep the other winding again, just one more time. Helical foil. Sweep AC resistance, go.
Solving Dowell's equation for inductor winding. 10 kilohertz. 100 kilohertz. 1 megahertz. 10 megahertz.
Okay.
Solution complete.
So now we're comparing this winding here, save that in blue, which is the flat windings on the inductor, with the red winding here, which is the foil, conventional foil. And you can see why everybody's using the flat winding solution, because at DC, it's just about the same. And then anywhere beyond about 15 kilohertz, you know, it's still better than the conventional foil winding. Okay, but we're not quite done yet. Not quite done yet. Let's go look at that winding again. Change it to foil. And then I'm going to ask the program in it to minimize the loss. What it's going to do now is going to use a conventional foil, but it's going to try different thicknesses. So it's going to make the thickness bigger and bigger and bigger until, they still come up with the same one. Sorry, let me make this deliberately force this to 0.1. So in this case, so for the flat foil winding for a buck or a forward, it wins every time. Doesn't matter how big you make the foil. So that's the right one. But I just want to do this case here where we make that foil smaller and we sweep the AC resistance again.
Solving Dowell's equation for
because this is
inductor
important,
winding.
getting back to somebody's
10
question, this is
kilohertz.
important for different topologies that
100
have
kilohertz.
a stronger AC component.
1 megahertz. 10 megahertz.
Okay, there we go.
Solution complete.
What did I do, run the same one there? 0.5, yes, I ran the same. I didn't update my file, sorry about that. You have to click update. 0.1, update. Sweep AC resistance. There we go.
Solving Dowell's equation for inductor winding.
One more time.
10 kilohertz. 100 kilohertz. 1 megahertz. 10 megahertz.
Okay.
Solution complete.
Now we have another winding structure, which is interesting. Let's save that in yellow. Okay. And this one here, we've used a thinner foil. For DC, for a buck inductor, it's not going to be good. But notice in this region here, if you're running an LLC at 100 kilohertz and it's only AC, then you're going to get 8 milliohms instead of 2.7. You get almost a 3-to-1 improvement if you wind it the other way with the foil the conventional way, but you have to use thin foil. So we went down from 0.5 millimeters to 0.1 millimeter, and then that design would be the best one for an LLC anywhere up to about 400 kilohertz. So now you got to think again. You can't take these nice flat wire inductors and put them in an LLC converter. I'm sure the magnetics companies already know that, but I don't see too many doing the flat foil design and then a very thin design. Because we're not filling out the window, of course, now we can actually shrink down the size of the inductor. So this is just another example of every topology is going to play this differently. And your job is generating these different curves and learning how to massage them around. And if it's a pure AC winding, so if it were a forward, a full bridge forward, a full bridge converter, or a half bridge converter, LLC or non-LLC, you're actually going to be better off sometimes with, you know, multiple layers of foil, depending on your voltage levels. Okay, so there's never one answer. There's never one inductor that solves everything. There's really cheap inductors that give you the price that you want. There's good flat foil inductors, which I do recommend for these buck converters. As the buck converter ripple goes up and the AC portion of the waveform goes up, that can change to where you want to start thinking about different structures for the inductor. So, you know, this keeps on going. You know, this is not so much research, this is applications. Every application is different. You learn how to wind with different structures and get these correct answers here. Okay, sorry if that was a bit confusing, but this is my point on this inductor for you. Coilcraft and Worth, if you're listening, you give me an inductor and in 5 minutes, I can give you the proximity loss model, okay? And it's a good model. Wouldn't this be useful to you if you're a user? Because now I'm not gonna try and stick this in an LLC circuit. Because when I simulate this values in here, it'll show me, no, that's not going to work. It's 3 times harder than if you wound it a different way. So one thing that we're looking for, you know, these models have been around for a long time. You know, even these circuit models have been around since 1993. Isn't it time that, you know, some of the vendors started giving us a good, you know, proximity loss model that we can run in LTspice? We don't really want to jump into another program and then derive the losses by looking at this chart and this chart and this chart. Just run LTspice like we do on a FET. LTspice as a circuit model gives us the losses. So here, so this is possible, it's quick. I did this just during the course of this webinar. If you want to load this in your data sheets, be my guest, put them in there. You know, we can do this for car losses too, but we do this for all of our transformers, our custom transformers that we wind, so that when we put it in a different application later on, we can see, is this going to be a good transformer? Okay, and it's not that complex a circuit. I haven't seen anyone following along with this yet. I've seen people starting to think about maybe adding 1 resistor for AC resistance. You need 5. Okay, that's the standard that was in the original paper, and that's the standard we found. You want 2% accuracy, you need 7 of them. So anyway, something to think about for you.
A lot of people asking about the loss in the gap.
Loss in the gap. Well, let's talk about that. All right. All right, if you want a way to build this inductor better, here's your core. Can I see myself here? Hold on a second, make sure I can see that. There we go. Here's your core, and they've gapped it right in the middle. All right, if I was designing this inductor, I would not gap it right in the middle because it's next to the windings. Okay, so there is going to be gap loss. So do we account for that? No. My advice is put the gap where it doesn't cause loss. And it's not hard to do. You just do an EI core here and you shift the gap down to the end. There's plenty of room in this winding, and then you shift the winding down the bottom, and there is no gap loss. So, you know, I kind of resist trying to do the gap loss analysis because my philosophy is you shouldn't have any. The gap should not be near the windings because I've seen how severe it gets. Rather than analyzing a poorly designed gap very close to the winding, design a better inductor, move the gap away. And that's what everybody does. You have to do this. You can't have a gap next to the copper. Rudy Severin showed this about 30 years ago. 3 gap lengths away is the rule of thumb. When you're in a buck inductor, does it matter? No, it doesn't matter because the AC is too small. If you gapped your core like that and you put the windings right next to it like that, this thing would probably fry. Okay, so just move the gap away. Again, my philosophy is don't analyze a bad situation, make a good situation, and then you don't need to do the analysis because you've eliminated the gap loss. Hopefully that answered the question there. All right, other questions to highlight, John? Let me just finish up my little presentation here. So this is the other winding possibilities that we talk about on here. And LLC inductor is the best one. In this case, it's only got the AC component. Okay, so you've still got to think about different structures. And I'm sure you'll be seeing some of these coming out, but it's really hard for the magnetics manufacturers to give you a standard off-the-shelf LLC inductor because everyone's got a different value. Everyone's hitting it with different AC current. They don't know what thickness of foil is going to be best for you. All right, more stuff to learn from. Go to ridleyengineering.com. We've got Ridley Works is doing all this. We do frequency response analyzers. We've got workshops, which will be reviving quite soon, actually, in a somewhat novel format. Facebook group, come join that. Current mode, if you like that. Power Supply Design Center articles, all this stuff on Dowell's is in there. Our past webinars are in there, so you can go pick up all the past webinars right here. So we'll have this webinar will be up there. It'll be the sixth webinar coming. We'll do another one in a few weeks from now. And of course, we've got our Ridley box, which everybody needs one of these. When you're in lockdown, you can have your own frequency response analyzer and Ridley Works at home and a scope at home. So you can do all these fun things. You can play around with these windings, primary, secondary windings, trying foil, trying wires, trying different layers, okay? It's a powerful thing to try it in the software, and then of course you go build the things as well to see how that works.
Put some red flags up before you, Ray.
Okay, I've got to look at the red flags because somebody flipped the temperature down a bit. Right, where's my questions? I'm going to bring questions up on the screen here. Great webinar, thanks a lot. That's good, it's like a comment I like. How do I sign up for your workshop? If you want to sign up for our coming workshops, please go to send an email to info@ridleyengineering.com. I see Greg Mary there. We've always also you're the first on the list. You're the first one we told about. And you flagged how to analyze these for interleaved inductor multiphase. I don't know. If it's a multiphase buck, it's all DC, so it's not very exciting, that particular case. Okay. Could you do with Litz wire example? We haven't put that in there yet. Yeah, you just have to go to the extra layers. We don't do Litz at this point. Okay, my advice on Litz is build it with solid wire. If you don't like the results, try the Litz in there. But I'm less than satisfied with Litz working the way it's supposed to, and that's kind of why I've a little bit stayed away from that. Comment on interleaving and relationship to the curves. Okay, yep. Let's see. Okay, that's a good question. There. Let's go to this. Can you see that screen, John? Yeah.
Yep.
All right. Interleaving is the half layer case, because obviously you can't physically have half a layer. But when you have a single layer design, you put half the primary one side, half the primary on the other side. That's what we call the half layer case. Okay, so at the top of the wire, the field's going one direction, the bottom of the wire is going the other direction. And that's the half layer case. Okay, and that you can see that the upturn doesn't come until later, and you've got about I don't know what it is there, about a 3 dB improvement when you go to the half layer case, or you go with interleaving. Now, when you go higher levels of interleaving, the objective is always make it so there's only one layer of primary or secondary before you put the other primary or secondary. Okay, so it's much better than that, doing that. Hopefully that answers that. Questions?
Flag one for you here, right?
Yeah, I'm trying to move my questions over. Okay. Which flag? So interleaving, we got that one.
Yeah, so can you extract 5 inductors and resistor values using the Ridley box?
You mean through measurements,
Yeah.
I assume?
Can you repeat the question?
Yeah, can we extract the inductor and resistor values using the Ridley box? Okay, measuring AC resistance is hard. So if you're down in the milliohm range, there's too much inductance in the setup for any analyzer. Even the old, Warhorse, the HP couldn't pull it out. Have we done that? Yes, we have. You can do it for transformers, where you can short the secondary and you can pull out the AC resistance. Okay. Once you get above a couple of megahertz, you start seeing a curve going up because you're not sensing it properly anymore. Yeah, but one of the features that we have that we're using here, we haven't handed it out yet, is if you can read in 50 values with the analyzer, you just click a button, it dumps into our software, boom, it spits out the model for you. So if you talk about, the old HP used to do curve fitting on LC filters and things, yeah, we can give you the values if you can give us a good measurement. And that will depend very much on what you're trying to measure on the Ridley box. It's got about the same resolution as the AP in doing these passive circuits. And it's just that trying to pull out these really low resistances in the presence of inductive paths is difficult. All right. PFC boost. The PFC boost inductor is interesting because it's got low frequency AC and high frequency AC. And what we see is the most common solution for that is just a toroid, an MPP toroid. Yes, it's got high-ish core loss, but the ripple is actually fairly small. If you go to a critical conduction mode converter, then you really got to start thinking about using a different topology for the PFC inductor. I would use a gapped ferrite for then. I would go back to that because there's going to be a lot of core loss on that one. But hey, you can do the same thing. We can do the analysis of it. We can extract the curve, and then you can put it into, so you could design that inductor in RidleyWorks as though it were for a buck. Lay out the windings, spit out the model, and then go load it into your PFC simulation. That's the beauty of these models. That's why I'm trying to tell the the magnetics manufacturers, where are we? Please give us this, and then we can put your inductor in any application simulation that we've got, and we can see if it's going to work in an LSC. Is this going to work in a PFC? Is it going to work in some kind of weird converter you got? If you can run the simulation, you got the winding resistance model, you can answer these questions, okay? But it's about time we did this kind of thing. The analysis has been around for 60 years. It's easy to go from this to the winding model. So why not do it? At least do it for yourself, even if we can't get it from manufacturers yet. So look at the winding structures, pull them apart, measure things, and then extract this. Any others, John? Windings in parallel. Yeah, that's a good one. That would be an entire webinar where we actually did a paper on this that we'll be publishing fairly soon on our design center. In general, you don't want to do two windings in parallel, like next to each other, and assume that, you know, nature's going to find the lowest loss path through those windings. But in general, this is it varies for every situation. But when you put two windings in parallel, and this happens with all the, you know, Dowell's equations and things like that, is you can't assume they're going to current share, and they won't. So the two windings in parallel, the currents will actually move to minimize leakage inductance on a transformer, for example, and they won't use the outer layer of winding. Okay. So when you're winding transformers, instead of doing two in parallel, you do the two wires in parallel, and then you do the second winding in series with that. So you're forcing conduction through both layers. That's what you're trying to do. Okay, so parallel windings, you have to be careful with that. But hey, you know, don't be discouraged by this. These are your tools for making your converter better, and they're powerful tools as well. But you can change these things. You know, if you need help, you've got a specific transformer, you say, okay, this is too much, you know, just call us. You know, we've got engineering resources here. This is what we do. We wind magnetics, we do different samples, you know, for people. This is, you know, familiar language to us. Good vendors can do this as too. I know lots of the magnetics vendors are on here who do really good work, custom work. Some of them also have our Coilcraft, have our design software. You can have these conversations with them. And they can help you with this design, but of course, you know, got the problem, they're busy doing everybody else's design too. So, you know, there you go. Let's see. Any comment about winding distribution, N and M? What will be the best scenario? I need to know all the waveforms, all the details, the wire sizes, the insulation that you need. Every structure normally has a different solution to it. And that is why, you know, you can't buy transformers online. You know, there's a few little flyback things for some canned applications, but everybody needs something different. Everybody's got a different number of outputs. Everybody's got different isolation requirements, temperature requirements. So this will remain custom power for a long time to come. It won't get standardized for a long time. Should I be zoomed out to capture many steady state switching cycles? Well, yeah, but we don't want to zoom all the way out because we've got startup. So you want to capture one complete cycle. So, you know, I do 10. You know, if you can zoom exactly on one and catch the edges, then it's going to be the same as if you caught 10 exactly on the edges. And then if you caught 100, you wouldn't have to worry about whether you captured the edges or not, whether you know. Why is it the green curve is a sum? I don't know what that means. My dream is to have a Ridley box. Yes, you should all dream of a Ridley box. Ridley box is great. I use it all the time. And I know times are tough right now. Everybody's looking at, you know, downsizing in their companies and so on. But, you know, that's why we've got this cost-effective option. And it's very portable. You can take it home. You can take it out to the customer. Your field apps engineer, you know, that's all cool. Corner frequencies and fitting the curves. Victor Subotin asked that question. It isn't quite done the way that you think it is. It's a very detailed mathematical analysis of a fifth order network. But frankly, it's beyond me. My summer intern solved that problem for me. You know, I've been doing this too long to solve fifth order circuits anymore. Does use of triple insulated wire, TEX-E, help in reducing proximity loss because of the larger spacing between the copper? No, it doesn't. TEX-E increases spacing to the secondary, but that's just increased leakage. I don't like TEX-E very much. I don't like the texture of it. And I don't like the temperature rating of TEX-E. So I use VIP wire, or I use custom wrapped Kapton wire. So New England Wire will make that as well. But the insulation on the wire only helps you in the fact that the wire has gotten smaller diameter because you got a whole chunk of insulation resistance on there. So the high frequency effect gets a little bit better. And yeah, there you go.
So Ray, you can't use the Ridley box to characterize the AC resistance of the winding, but you can use it to characterize the inductance of the resistor.
You can use it for measuring the AC resistance of the winding, but I can't guarantee it's accurate.
Right.
So the paper that we're going to post fairly soon, it's good out to about 1 megahertz. So what I would do with that is I would put some AI on top of it. So, okay, look, it's gone through the transition region of the multiple layers. Now it's going up with a 1/2 slope, and suddenly that 1/2 slope started curving up. I'd say, okay, well, let's flatten that data to a 1/2 slope and then curve fit it. So, you know, this is one of the most difficult measurements to make on the magnetics. So you can do it, but, you know, we do the calculation and the measurement to make sure that the measurements are good. Okay, so not easy things. And then Beaulieu, complex numbers, blah blah blah. Yeah, it's too advanced for me mathematically these days. That's why I have interns to answer those complex mathematical questions. RL1 duplicated with RAC. I don't know. It all works. Does the inductor design tool account for this? Yes, it does. I say we just analyzed this Toilcraft inductor on the fly there. So if you do some really weird structures, no, you've got to go to finite element. If you go to finite element and you can plot an AC resistance for us, send us the data. We need 50 points. Here's the model for you. That's not a problem. There you go. All right, in the first transformer winding, we split the primary winding. So we did half the primary, then a secondary, then the other half the primary. What that does is it reduces the field strengths. So instead of going through 2 layers and get a field strength of 2, I only go through 1 layer, and then the field strength hitting the secondary is a strength of 1. So the proximity loss, which are excited by those, you know, field strengths between the layers, is cut in half, and then that means the proximity loss is cut down by I squared. So it's cut down a factor of 4. That's why these AC resistances climb so rapidly, because you get current circulating and it's I squared R. So phase splitting the windings is always good. So primary, secondary, except that when you split the windings to halve the leakage and cut down the proximity, you increase the capacitance, okay? And then when you've been doing, you know, if you've got lots and lots of windings, you know, having 10 primaries interleave with 10 secondaries, it's like, yeah, it's wonderful proximity, but you might have a couple of nanofarads of capacitance, you know, from primary to secondary, and then your EMI is impossible to solve. So there's a trade-off. You know, some of the magnetics that you buy from Peyton Magnetics, you can see they've hit that trade-off. They've done a secondary, a stack of primaries, and then a secondary, because the penalty of the capacitance is just too high for the converter. So you've got to trade off keeping these losses low and keeping down your capacitance of the structure. Helical foil with 1 layer but thinner copper. No, it doesn't help. It doesn't help because thinner copper will just raise the resistance. So you just end up with less conductor at all frequencies. So the whole curve will shift upwards if you use thinner foil in a helical inductor. Now this particular Coilcraft inductor, they could have made it thicker, but it gets to this capacitance thing again. If you use thicker foil, the windings are crammed against each other and then the capacitance goes up quite a lot. So the resonant frequency goes up. So you've got this trade-off. It's nice to space the flat planar windings out a little bit. Also, when you wrap foil around the bobbin, instead of, if you don't do them with the flat foil, if you do it with normal foil, if you use thin wires, don't cram them up against each other. You use a thin wire and then lots of insulation to fill the space before you get to the next one. And then you get low capacitance and low RAC as well. Any other questions you see, John? Don't know the exchange rate into Brazil. You can probably Google that one. Can you comment why Google by Colorcraft has cut away the core on the edge of the SER29 blah blah? Okay, I'm not seeing that in here. I'm looking at the core here. Yeah, I don't know what part of the structure is original and what is theirs, but presumably it's just for entry and exit of the copper wire. We've done this. I'm sure it's well thought out. You just need a certain number of turns, you need a certain inductance, and then the rest is mechanical to figure out how to terminate these things cost effectively and do a good job. In the current slide, REC is increasing, but LAC is random. Yeah, that seems weird, doesn't it? You do see strange effects sometimes. Sometimes you see a linear drop of the LAC, but then sometimes you'll see that the L can almost stay constant, and then sometimes it actually drops. And then in some of the curve fitting models, we saw that the last inductance sometimes becomes negative. So we didn't let that happen. We force it to zero. But yeah, we're curve fitting a fifth order network to a complex curve. And sometimes it can do unusual things. So it's not always predictive of how the inductor is going to drop with each one on each stage. If it's a very lossy inductor, it's very predictable and makes a lot of sense. But as the efficiencies go up, you know, it does things that will surprise you. What is the best strategy to reduce the proximity loss? Use Ridley works. That will reduce your proximity loss. It depends. It's all on the topology. If it's a pure AC inductor, then you've got to keep the AC resistance low. You keep the layers low. Okay. So there's lots of different ways for doing that with different core structures as well. So you do see quite interesting structures coming out on some of the more advanced LLC converters. They're not using conventional looking inductors in there. There's a lot of foil coming in. There's winding on 2 legs instead of 1 leg. So, you know, it's kind of a fun area to play with. Clarity and simplicity. I appreciate that, Stephen. I hope it's clear. Sometimes I look at this and to me it's so transparent what's going on, and sometimes I look at it, it's like, wow, this stuff is really quite complicated, but it's not. It's, you know, it kind of every topic that we deal with in power electronics is quite similar. It's like if you stop thinking equations and you start thinking curves, your life is better. And for most of us, we've got a lot of design to do in a short space of time. You can't be enmeshed in the equations. It doesn't make sense. You know, people solve the equations for you so that you wouldn't have to. That's the idea of this. We solved them for you so that you don't have to solve proximity. You can get the free version of our software free, not free obviously, and that does the buck converter. So if you're making buck converter inductors, you can go solve for your buck inductor, and magnetics vendors can get the models out there, you know, for free. That'll be cool. What's the main purpose of interleaving with planar transformers? Well, planars are very complicated. If you have primary, secondary with same turns count, and you put a helical primary with a helical secondary, it suffers the same thing where all the current flows towards the middle. When you change the turns count, the primary is going to pull the currents to different places, and then the only thing to do with that really is to go to finite element methods. So, you know, go hire the universities, grab a student and say, hey, look, can you analyze the structure for us? And if you can send us the AC resistance, we'll send you back the model here.
That's the price of the software, right?
Price of the software? The 1-year license, I think it's 400, is it, Denise? Something like 400. It's $1 a day. For those of you that say, well, I'm going to solve proximity loss all by myself and do that, you're looking at about a month. And I know that because I did it. So, you know, you've got a trade-off. Do I really want to go dig into those questions of how that proximity loss equation works and solve it myself, or do you have a job to do? in which case getting our software is, you know, going to speed you to the answer. And even if you want to, 500? Oh, 1 year license is 500. If you buy a Ridley box, you get a lifetime license, lasts forever, coming along with the box. And then we're constantly updating this. Basically, every time we do a webinar, I find a new neat little feature to put in. So while we're waiting for that sweeping of the proximity losses, I said, well, it'd be kind of nice if it talked to us so we all know something's going, instead of looking at just a little counter in the corner of the screen. So we changed that too. Can I verify Fourier solution? Yeah, the Fourier solution. I see John has answered this. The Fourier solution, it just happens in the time domain. You only need Fourier if you're doing post-analysis. But you're hitting the model in the time domain. The switching waveforms are there. Okay, so you don't need any Fourier. That's the beauty of the time domain simulation. And it still seems a little miraculous to me that we fit this curve in the frequency domain and then you run it in the time domain and the losses come out correct with all the Fourier expansion. That's like magic. But I'm sure Mr. Fourier and Mr. Laplace would have something to say about that. And also I had that conversation with Dr. Vulperian as well. It's like, you know, why does this work so well? He said, well, it's causality. If it matches in the frequency domain, it's going to match in the time domain because it's the real world. Everything's in the real world. Even the frequency domain is a measurement at a frequency point, which is kind of like doing Fourier analysis. Okay, but yeah, LTspice is really your friend on doing this, and I'm amazed how fast it can go on such high order circuits. Okay, and then when we put core loss in, we put in another 14 L's into the model to do core loss as well. Maybe we'll repeat this this webinar with core loss too, even though that one's a little bit more hairy to get your mind around. I think there's not any questions left. Somebody asked about mutual impedance, and you know my answer to that. No, I don't know what it is. I've seen you talk about it. I've seen you do it. I don't have the bandwidth in my brain to explore that at this point. I'm trying to build out these models of proximity loss. I'm really trying to get some participation. I mean, again, Coilcraft, Worth, if you're still there, why wouldn't you give your customers this? We really want it. Everybody wants to use LTspice and run these models. But unless we got momentum on these simple things like doing proximity loss, then moving on to higher level things, you know, is going to be tough. But you know, I'm at least the third researcher to discover this model and say, hey, this is really good to use this. So hopefully everybody listening here can start thinking about this. But again, if we can get the magnetics manufacturers to hand out the model, I mean, in these days, if you want to sell somebody a FET, people aren't going to buy them unless you have the SPICE model. And there's no reason why we shouldn't have that same scenario for inductors. It's like, okay, you made a standard off-the-shelf inductor, and we have the SPICE model. And it'll be nice to do that. It's not that hard, and of course we'll help you do it as well. Just trying to move things forward from, you know, 1890 basically on models. When we had the basic transformer model, we're trying to improve on that and include the, you know, the proximity losses as part of it. Any more questions coming in, John? Yeah, we've got 161 of you still on the webinar here, so hopefully we're entertaining you. I can't see anything there.
I like Art's comment.
What was Art's comment? Did you see what was Art's comment?
One of the last ones.
Okay. Arthur nice. Ridley works frees us from being mathematical slaves and lets us do more engineering. Okay, Art, I really appreciate that comment. Now, remember, I'm not the first person to try to do this. When Dowell did his work and they published the curves, that's exactly what they were trying to do. They were trying to release you from being mathematical slaves. Okay, when Bodie swept a loop gain, that's exactly what he was trying to do. It's like, people stop trying to analyze this 50th order vacuum tube electronic control circuit. Draw a picture and you're done, okay? And then learn how to shape these pictures and these curves. That's what engineering is. That's what engineering has lost, it seems to me, in the teaching process these days. You know, people aren't, that they want to be mathematical slaves. And that's all part of the research environment. But pushing the curves around it's where the fun is, quite honestly. I don't like math. Might surprise people. I really don't like math. Core loss with LTspice. Well, Eric Pratt. Let me just give you a little teaser for the next one. Maybe we'll do this next time, okay? And go there. Can we do core loss with LTspice? And do that. Let's go look at our transformer. And we've just done winding loss. Let's look at the core material. Right there. Boom. There is your LTspice model for core loss. Okay. So yes, it would be nice. We've had that in the software now for about 2-3 years, I think. You get unusual values in here. Notice these inductors are 1.8 henries, 11.5 henries, and 2.9 gigohm. Okay, and these ones are coming in really high values because this is a high voltage input. Okay, so you got 500 volts up to 700 volts being applied to this, so obviously you're not going to have big resistors in here. But this is the dual of the winding loss model. Okay, it's almost like a fractal network, not really, but it's a repeated network. And at different frequencies, different values of resistor kick in to predict the core loss for you. So yeah, I love this. I don't look up core loss charts anymore. I just go in here, I can look at different materials. It's like, okay, PC95 is that, and the values change. PC90 is this one, and the values change. PC47, here's the total loss, and then here is the core loss model for you, okay? It's not as accurate as the proximity loss for the simple reason that the measurements of core loss are not accurate. Nobody has a comprehensive, or very few companies have a comprehensive set of measurements. And when they do a good job, they say it's typical. And that sends red flags off to me. It's like, okay. And sometimes it's 20% more, sometimes it's 20% less. So it's good as, you know, the core loss data is. Do we use our tools for multi-stage bucks? Well, a multi-stage buck, you design it as a single stage. Could we do it? Yeah, that was my master's dissertation, was the multi-stage buck converter. That was way back in 1986. So yeah, we can certainly do it, but nothing really needs to be done there. I mean, everybody's building multi-stage. The app notes work, the demo boards work. It's just a buck converter. Okay, so, you know, designing the inductor, sure, go in there and design the inductor. Right. That's it. Okay, Eric, I see you got the answer there to the core loss. By all means, get the software, give it a try. Core loss webinar, same person. The core has its behavior with permeability versus frequency. The proximity loss doesn't care what's going on in the core. The results you get for analyzing proximity loss is independent of a core structure, unless you're creating a gap and you're putting a concentrated field, you know, into the windings, which you shouldn't be doing. So I'm not going to analyze a bad situation for you and put it in the software, because, again, I said this before, you shouldn't do the bad situation to start with. There you go. I think we've got all the questions here. So it's 11:30. I appreciate everybody's attention here. I hope you enjoyed that. Please send us some feedback, info@ridleyengineering.com. We'd like to hear that you liked it, because engineers are typically very quiet when they like things, and when they find a mistake, they're very noisy. So we do like to hear that we did a good job. If you have any comments about style, the things that we do, what you'd like to see in the future, please send that to us. You will receive an email coming up about the recording going online, and also about the next webinar that will be coming up in just a few weeks. So thank you all for coming from all around the world, and I hope you have a great rest of the day, and we'll see you again soon. Thank you.